Welcome to Electric Flux Part 3, and in this we are going to stress on the symmetry of flux, how to find flux, and finally Gauss Theorem and probably its applications. So we'll move on. We know that flux is a scalar quantity. We also know that for a point charge, the flux is q by epsilon naught and distributes isotropically in space. Considering these two things about flux that we already know, we can use these two concepts to find out flux through various objects and various things. Let's start with some things that are simple. Let's consider a hemisphere that is closed from all sides. We are considering the entire surface. This is the curved surface of the hemisphere and this is the flat surface of the hemisphere. And we are going to ask a few questions here. The first question is, what if I put a charge just inside the hemisphere? What will be the flux through the hemisphere? What if I take another hemisphere and put a charge just outside the hemisphere? What will be the flux through the hemisphere then? And what if I take a third hemisphere and put a charge exactly at the boundary of the circular surface of the hemisphere? What is the flux going to be in all these cases? So we know that a charge produces a flux q by epsilon naught, and all that q by epsilon naught, whatever it is, howsoever it is going to pass through the surface of the hemisphere, either the curved surface or the flat surface. So in this first case, we can say that the flux through the hemisphere is q by epsilon naught. Moving on to the second scenario, if the charge is outside, we will see that the field lines, I had told you before that flux can be compared to, not exactly is, but can be very easily compared to the number of field lines. So in this case, you have field lines, let's say 1, 2, 3, 4, 5 lines that are entering the hemisphere, and there are some other field lines also that are not exactly entering the hemisphere, like these. Now the total number of field lines or the total flux is obviously q by epsilon naught, but what about the flux that passes through the hemisphere? So we shall see that if 1, 2, 3, 4, 5, 6, sorry, not 6, just 5, 1, 2, 3, 4 and 5 field lines enter the hemisphere at these points. You can see these points. Let me mark them in white again. All these field lines enter the hemisphere from at this surface, and they leave the hemisphere at the curved surface. So if number of field lines entering here, they enter, at this point they enter, and at these points they leave. And if the number of field lines entering the hemisphere is equal to the number of lines leaving the hemisphere, we say that the flux is 0. Let me write it. If the number of field lines entering equals to the number of field lines leaving, then we'll say that the flux is equals to 0. So in this second case here, the flux is equals to 0. Now what about the third case? Now you can see that some field lines they pass through the curved surfaces, some field lines they come out of the hemisphere, sorry, they don't all pass through the hemisphere, they just pass from the lower side. And let me draw the charge, let me reinforce the drawing on the charge, right. And there are some field lines, a few of them, which are going parallel to the hemisphere like this. So if we had two hemispheres which would actually make up a complete sphere like this, the total flux through complete sphere would be q by epsilon naught. But we know that half of them are passing from this hemisphere and the other half are passing from this hemisphere. So we can very easily say that the flux through the hemisphere is q by 2 epsilon naught. Now let's consider a cube, and I'm drawing a cube here freehand, so you may expect it is going to be a very bad drawing. Anyways, let's consider a cube. If I want to see this cube from this line of sight, it would become really simple to analyze. This is my cube. This would be my cube. There is a charge at the center, let's say. We can also draw a charge here at the center. Now you are being asked, what is the flux through the cube? What is the flux through the cube? And what is the flux through each face of the cube? So you must understand at this point that flux through the cube is basically flux due to this charge, and any number of lines, let's say we have 100 lines, and any number of lines that the charge emits basically pass through the surface of the cube. Any number of lines that the charge emits passes through the surface of the cube. There is no escaping the cube. There are no lines that can escape the surface of the cube. So the first answer, what is the flux through the cube, is very easy, that is q by epsilon naught. That is the answer to the first one. Now considering the second question, the most important question of this here. Second part of the question, what is the flux through each face? Now we know that the charge is placed exactly at the center, and all the faces are at the same distance, they are very symmetrical, and this is where the problem in symmetry comes in. Electric flux is all about symmetry. If you can understand symmetry, you will get to solve the questions on electric flux. So, since all these faces are symmetric, and how many faces does a cube have? So let's count the number of faces first. So this is A, B, C and D and E, F, G, and there is a hidden one. So the hidden one I am going to draw with a different color. Okay, so this is, let's say, H. So how many faces do we have? We have 6 faces in a cube, and through all those 6 faces are equidistant from the charge. They are symmetrical to the charge. So we can say that through all faces, that is the problem of symmetry here, through all faces the flux is equal. So if through all faces the flux is equal, through any one of the face the flux is definitely going to be Q by, how many number of faces there? A cube has 6 faces, so the flux is going to be Q by 6 epsilon naught. Now let's consider some complicated problems here in the cube. I have a similar cube, again freehand drawing. And now let's say that I have a charge at one of the faces. Let me first draw the points on the cube. A, B, C, D, of course, and then we have E, F, G, and the hidden one is H. Now we have a charge not at the center of the cube this time. We have a charge at the lower face, this face, Q at the center of face. What face? Let's say DC, G and H. The Q is at the center of the face DC, G and H. Can you see the face DC, G and H? I'll mark it with arrows, DC, G and H. This is your face. I can even use a color to distinguish the face if you want. So this is your face basically. The cube is at the center of this face, this lower one face here. Now the question is, what is the flux through the cube? And that is the question. So if we can draw a two-dimensional diagram, would be good at this point of time. So we have a cube like this, and there is a charge somewhere here, because this is your line of sight, as you can see, so you won't be able to see that face clearly. So this is the charge that is over here. Now thing is that if we put another cube, below this charge, below this cube, what do we have? What are we going to have? Let me put the cube here also, so that it becomes a bit understandable. So if I put a cube, another cube, just below this cube, same size, same dimensions, everything same. So what we are going to experience is this, that whatever flux the charge emits either passes through the lower cube or it passes through the upper cube. There is no denying there. It either passes through the lower cube or it passes through the upper cube. So if the flux through the combined two cube system, flux through 2 cube system is q by epsilon naught, because all the lines that the charge emits, this charge here, or all the lines that the charge emits either passes from the upper cube or pass from the lower cube. So the flux through 2 cube system is q by epsilon naught, and both cubes are symmetric. That is the second reasoning. Both cubes are symmetric. Both cubes are symmetric. Same size, same dimensions, equal distance from the charge. So the flux through any one of the cube is going to be q by 2 epsilon naught. So the flux through the upper cube, let me bring back the diagram that we had. The flux through the upper cube is q by 2 epsilon naught, the flux through the lower cube is q by 2 epsilon naught, and the entire flux is q by epsilon naught. So this is the second part of the problem. Now let's consider another cube. Again, freehand. If I have a charge at the center of an edge, let's say A, B, C, D, E, F, G. Now H is not visible, I'm not going to show it right now. Is at the center of the edge BF. Now what is the flux through the cube? Now, in order to fully cover the charge completely symmetrically, how many cubes do we need? We can have a cube like this. I'm sorry. Let's go. And then we can have 2 cubes above it. So the 2 cubes above it, I'll show it in blue. Now we see that our charge is completely and symmetrically covered by 4 cubes. So if you draw a 2-dimensional diagram, okay, let's come back to this diagram. In order to cover the charge, in order to cover this charge symmetrically, you need 4 cubes. And now when you have covered it with 4 cubes, the entire number of field lines, whatever their number is, they may be 10, they may be 100, they may be 50, does not matter. The entire number of field lines are passing through all the cubes, and there is no cube that is left open, or there is no cube that is not being covered. So we have total flux through 4 cubes is q by epsilon naught, because all the field lines that the charge can emit, whatever their number is, they will either pass through the white cube or the yellow cube, white cube or the yellow cube or the 2 blue cubes. There is no escaping that. And if the situation is absolutely symmetric, the flux through each cube will be flux through each cube, flux through, let's say, the white cube is going to be q by how much? 4 epsilon naught. And why is that? Because the arrangement is symmetric, and by principles of symmetry we have found out that 4 cubes need to cover the charge. Likewise, we can move on to a further even more difficult problem. Let's say and there is a charge at the corner edge. Let me mark it A, B, C, D, E, F, G. H is not visible, I'm not going to draw it. So charge is at B. And what is the flux through the cube? That is the question. What is the flux through this cube? Again, the principles of symmetry come into play. How many cubes do we need to actually cover the charge completely? So if we have a cube like this, and then we might have another cube like this, and then we might have another cube like this. Now I'm not going to draw any more because this is sufficient enough to understand. So let's say that I have drawn 4 cubes like this. Now the question is the charge covered, totally covered, or there are still field lines that can escape into the space without crossing any number of cubes? So I have 4 cubes right now, just drawing this in bold, and here is your charge. Now in this particular arrangement you will notice that this charge here will have 2 kinds of field lines, one that will pass below and one that will pass above. So let me draw the type of field lines that will pass below like this, and you will also have field lines that will not touch any cube and they will pass above. So there is a boundary surface. If you can see the green arrow, there is a boundary surface. If the total number of field lines are, let's say, 100, the 50 field lines pass below and the rest 50 will pass above, in all directions of course. So how many more cubes do we need to cover this entire charge? So we need an arrangement exactly like the lower arrangement. We need an arrangement exactly like this to cover this entire thing. The number of cubes that need to be covered, number of cubes needed to cover the charge symmetrically. Now this is very important, symmetrically is 8. 4 below and 4 above. I have drawn only 4, the below ones, I haven't drawn the 4 above ones. The diagram is going to be very complicated, but you will understand that there is a boundary, there is a surface here, there is a surface here. Let me mark the surface with, okay, so let's say this is the surface here. This surface here. So 50% of field lines will go below the surface, they will go below the surface, and the rest 50% of the field lines, they will go above the surface. So how many cubes do we actually need? We need exactly 8 cubes. So what is the flux through each cube going to be? Flux through each cube will be Q by 8 epsilon naught. There are some really interesting questions that we can solve also where flux doesn't directly appear in the question, but you can take the help of flux to solve a question. So let me jump in straight to the question. There is a square surface. There is a square surface here. And perpendicular to the square surface, perpendicular to that square surface is a charge. Let me do the charge here, is a charge q. And the square surface is also charged. The square surface is also charged. Its surface charge density is sigma. You know what sigma is? Sigma is charge per unit area. So this is a square surface. You can see the square surface. There is a charge here. The square surface is itself charged. The square surface charge is q upon area. And this is the question. And the question is really very interesting. What is the force exerted by the charge on the square surface? Here is a square surface. The charge is q. The square surface has charge density sigma. And the question is very simple. What is the force exerted by the charge on the square surface? And some values have been provided to you. What are the values? The side of the square is a, and the distance from the center of the square to the charge, from the center of the square to the charge is a by 2. This distance is a by 2, half the distance. And this is the question. Now, how do we attempt to solve this question? You can do a lot of things. You can do integration and stuff. You can take force due to square plate on the charge. You can take force due to charge on the square plate. But I'm trying to solve it using a very simplistic means. Let's see how it works. Let me take the square surface again. So we have a square surface. Okay, so let me close the square surface. Nothing should be open. All right. Now let's see if we can fill it with a color. Yes. Right. So this is our square surface. And from the center of the surface, there is a charge here. And the charge is q. Right. Let's consider an area. Let's consider an area here. And let's consider a very symmetrical area here. And let me fill this area also with some different colors. And this one. Now, there will be a field due to charge q. There will be a field due to charge q. And why am I saying that the area is symmetrical? I am saying that the area is symmetrical simply because the distances from the center of the square are equal, and that is equals to x. So the field due to charge q will be E and E in this case. And let's say that the area, any of those areas, is dA, very small area. You must know what is force. Force, by definition, is q into field. We are considering the field. We are considering the field due to the charge q. I remove this q and I say that the charge q into E. Right. So this is the formula. Force is q into E. Now, what I am trying to do here is this. I am trying to find out the field due to charge q. And then I am trying to multiply this with this green charge here. You know that the entire square surface is actually filled with charge. That is why the surface charge density of the square surface is sigma. So what is the q here? The q of the green charge. This q of the green charge. So q of the green charge is sigma into small area, that is dA. And then we have the field. and this is the force. And we must also know, this is quite understandable, that force and field have same directions. They are parallel if the charge is positive. They are anti-parallel if the charge is negative, but they are parallel if the charge is positive. Now you must try to understand here that the force is always going to have two components. A component that will be vertically downwards, that we will call as Fy, and a component that will be parallel to this surface, and that we are going to call as Fx. Likewise, there will be two components here also, Fy and Fx. And what do we notice about Fx? We notice about Fx that Fx are equal and opposite. Since they are symmetric. You can draw Fx here also. This will be, let me show you. This will be the direction of Fx on both charges. And you can see that both the Fx are equal and opposite, and they will get cancelled out. Whereas both the Fy are downwards and they will get added up. So what kind of field do we actually need, or what kind of force do we need? So we need the force along y-axis, and the force along y-axis, if you take this angle as theta, and since they are symmetric, this angle is also theta. The force along y-axis for one of them would be sigma into dA into E into cos theta. Sigma into dA into E into cos theta. Now sigma into dA into E is the total force. Cos theta is the downward component, you can see from the right angle triangle. This is your right angle triangle. So cos theta component is basically the downward component. Right. So the force along y-axis, this is going to be your force along y-axis. This is going to be a force along y-axis. Now you might be thinking that we might have to actually integrate it or do something about it, but no, this is a very simple thing to do. Consider this over here. You have sigma into dA into E into cos theta. Now what is area into E into cos theta? Area into E into cos theta is basically the flux, the small flux that passes through this area, or the small flux that passes through this area. So we will call that flux as d phi. And when we want to add all the forces, all we have to do is to add this d phi. Sigma gets out of the scene, d phi, and that is going to be sigma into phi. Now we come to the final part of the problem. What is going to be this flux? We need to find out the value of this flux. And if we can find out the value of this flux, we know the force that will be acting on the plate. So in order to find out the flux, we have to draw the square plate again. Let's see, this is my square plate, and I'll remove a part here. Okay, so this is my square plate, and I have to fill it with some colors here. So let's see. Okay, so this is it. Now if this is a square plate, what I can do is this. I can create a cube around this plate. Use a different color. I can create a cube around this plate like this. And removing this part. Okay, so I have created a cube around this plate. So there's a cube around this plate, and you know that the charge was here at a distance of a by 2, where the side of the cube is a, this side of the cube is also a. And the question reduces itself to a very simple thing. What is the flux of Q through the blue surface and you know that the flux of the cube through the blue surface, which is one of the faces, basically a face of the cube, is going to be q by 6 epsilon naught. And why do we know it is q by 6 epsilon naught? Because every cube has 6 faces. Every cube has 6 faces, and the charge, this charge here, is placed symmetrically. It is equidistant from this face, this face, this face, all faces. So the total flux of this charge, we all know that the total flux of this charge is q by epsilon naught. If we take all the field lines everywhere in all directions, the total flux is q by epsilon naught, and the flux through one face is 1/6 of that, that is q by 6 epsilon naught. And the force becomes, do you remember what was Fy? Fy was simply equals to how much? Sigma into the flux. So sigma, and what is the flux? Q by 6 epsilon naught, and that is your force. Now this is a topic, Gauss theorem, the most important theorem in electrostatics. Not very usable though, but yes, very important, and a lot of questions are being asked on this. So we will first understand the difference between an open surface, and the difference between a closed surface. In an open surface, you could take area perpendicular, area vector, and that perpendicular could be anything: perpendicular up, perpendicular down, perpendicular forwards, or perpendicular backwards. The only condition is that it should be making an angle of 90 degrees with the surface. Only condition, angle of 90 degrees with the surface. That is the entire condition there. In a closed surface, there is a rule that you can take perpendiculars only outwards, area vectors only outwards, not inwards, never inwards, and this is something that you have to understand. So I'll write this: in closed surfaces, the area vector is always pointing outwards. We have to understand this much. It is still perpendicular. I'm not saying it is not perpendicular. It is still perpendicular, but it is always pointing outwards and never inwards. Never inwards. Never do that, please. In an open surface, you can point in any direction because there is no outwards or inwards. Whereas in closed surface, you will always have to point it outwards. We have to understand what Gauss theorem is about. And in order to understand what Gauss theorem is about, we must understand what is a flux. So we take a closed surface and let's say we have a closed surface. Any shape, any design, does not matter. Now there are two types of charges, one that is outside and one that is inside. I'm not saying there's just one charge outside or one charge inside. There can be a combination of charges inside, and there can be a combination of charges inside. But okay, let's first simplify things. Now, if we consider the charge outside, we have to understand that the field lines that the charge emits, some of them are passing through the surface, obviously. Some of them are not passing through the surface, obviously. You can see very well. Some of them are passing through the surface, some of them are not passing through the surface. And whatever field lines are passing through the surface, let's count the number. It is 1, 2, 3, 4, 5. So 5 field lines are in, 5 field lines are coming in from here and going out from here. Can you see that? If 5 field lines are coming in from here and going out from here, we know very well what it says. if number of field lines in equals to number of field lines out, then flux of that charge is equals to 0. So let me call this charge as A charge, and let me call this charge as B charge, and we will say that the flux of A charge is equals to 0. Now let's come to the B charge. What is happening in case of B charge? Assuming that it is a positive charge, and you will focus only on the yellow lines right now. In all cases and in all circumstances, from the surface you will see, either you can see here, 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 or here. Let's count the number of field lines. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 field lines are only coming out of the surface. The flux through the yellow charge is only coming out of the surface, and if it is only coming out of the surface, there is going to be a flux, and the flux of the A charge is going to be Q by epsilon naught through the surface. So we can understand this again. If we have a surface, closed surface, and we have two kinds of charges, one is outside, one is inside. For the outside charges, the field lines they enter and they leave. If they do both things, enter and leave, we will say the flux is 0. And if in case of yellow charges, you might see that the flux of the field lines only leave. You take any field line, you will see that the flux only leaves. And in that case, if it is only leaving flux, we will say that the entire flux of this charge, the entire flux of this yellow charge is leaving the surface. And what is the entire flux of any charge? The entire flux is Q by epsilon naught. So we understand one point here, and that point is very important. That is, in a closed surface, the flux due to outside charges is 0, and the only flux that exists, that exists is due to enclosed or inside charges. And this is what we call as Gauss theorem, qualitatively speaking. This is what fundamentally Gauss theorem is. There are many complicated equations to it, but we'll study that. But this is what Gauss theorem is. Flux due to an outside charge enters the surface, leaves the surface, and it is 0. Flux due to an inside charge leaves the surface, or if let's say there is a negative charge, let me draw a surface here, and there is a negative charge minus Q, the flux enters the surface, only enters the surface, it doesn't leave the surface. If it only enters the surface, the flux is going to be minus Q by epsilon naught. But whatever flux is on a closed surface is only due to the enclosed charge. So now we come to the mathematical aspects of the Gauss theorem. Again, going back to a surface, and then talking about, let's say, a charge outside, and let's say a charge inside. And what do? We consider a small area. You might see that the area vector is in this direction. And there will be two field lines. The field lines due to the red charge would be something like this at this point, obviously, at this point. And the field due to the green charge would be, let's say, something like this. Let me call this as field due to out, and let me call this as field due to in. Let me draw the surface again. Okay, very rough, but okay. So this was the charge outside, and the field due to the charge outside was something like this, and the field due to the charge inside was something like this. And we find out the net field at this point, this area. We find out the net field at this point. So let's say the vector sum comes out to be something like this. This is E naught. So the vector sum of E outside, E inside, E is equals to E in plus E out, the net field. And we can see that there is an area vector over here. So if we have E like this, we can find out the flux, E dot area. And since it is a small area, I am going to take it as dA, not A, I am going to take it as dA, E dot dA. And now we are going to do the same exercise for all points on the surface, And what is this exercise? This exercise is basically finding out the flux due to the net field. Let me remind you, the net field, very important to notice, net field and the area vector. The flux is net field and the area vector, and we find out the overall flux for all points on the surface. And since we are doing for all points on a closed surface, we mark a circle on the integration. This circle always represents a closed surface integration. Closed surface integration. And when we are going to integrate it, please don't get any ideas. We can never integrate it. It's not integrated, using basic mathematics that we know of. It's really difficult to do that. But if we somehow integrate it, for some reason we could use a supercomputer, whatever you want to use. If we could integrate it, we would get the overall flux. And you know that what overall flux is. The overall flux is only going to be due to this charge here. It is not going to be due to this charge here. So the overall flux is going to be Q enclosed divided by epsilon naught. So if this Q enclosed is, let's say, Q2 and the outside charge was Q1, the flux is going to be Q2 by epsilon naught. And that is what your Gauss theorem is. Let me write it very properly again. The flux of overall field, and I cannot stress it enough, it is not field due to inside charge, it's not field due to outside charge. This field here is the overall field. Flux due to overall field is only equals to Q enclosed divided by epsilon naught, and that is your Gauss theorem. So we will talk about this, just a revision point. So this is our closed surface, and now I am keeping a few more charges. Let's say this is Q, this is minus 2Q, and this is 3Q here. Now if we want to find out the field at any point on the surface, let's say I have to find out the field at this point on the surface, and this is the area vector, of course, dA, and the field direction is something like this. This field is due to all charges, inside or outside. And when we integrate the field E dot dA for the entire surface, for this entire surface, this flux comes out to be then Q enclosed by epsilon naught, And what is going to be Q enclosed here? It's very simple. The Q enclosed value is Q minus 2Q by epsilon naught, and that will be minus Q by epsilon naught. And what does this minus mean? Minus mean is that the net flux is going into the surface. So if I have a surface like this and there is Q and there is minus 2Q here and there is 3Q outside also, but the net flux, whatever the net flux is, it is going into the surface because the negative charge is greater. This topic is about the explanation of Gauss theorem, and we can see that we have an XYZ coordinate system. Let's say this is Z, XYZ coordinate system, and in that coordinate system there is a cube, and if the side of the cube is, let's say, A, you can very well point out the coordinates of the cube. This one is A comma 0 comma 0, but I'm not writing it. This one is 2A comma 0 comma 0. This one would be something 2A comma A comma 0. This one would be A comma 0, and this one here would be 2A comma 0 comma A, and this one would be A comma 0 comma A. So there are a lot of points here. Field lines in this region. The field lines in this region are parallel to x-axis, and the field lines in this region are given as Cx I cap. What is C? C is a positive constant. What is x? The x coordinate. And I cap represents that E is along positive x-axis. And there is a question. The question is very simple. Find the enclosed charge inside the cube. So how do we find the enclosed charge inside the cube? Now if we look at the cube very carefully, you will see that there are some faces like this one. Let me draw the face. This is x-axis, this is y-axis, this is z-axis. I will have to draw the cube again. I'm sorry, but yes, I have to draw the cube again. There are some faces on the cube on which there will be no flux. Let me show you how. For example, this face here, the top face, can you see? The flux on the top face is going to be 0, and why is that? That is because the area vector of the top face is perpendicular to the field, and E dot A is going to be 0. If we don't want to understand this numerically, we are going to simply say that the field passes parallel to the surface, hence the flux is going to be 0. Likewise, there is going to be a bottom face, this one. Again, the flux through this face is going to be 0 for the same reason. The electric field is perpendicular to the area vector. There are more faces. I'll have to show them in a different diagram. So you have to draw the cube again. About the front face, that is basically facing you. About the front face, let me show you the front face. This is the front face, and the area vector is outwards parallel to z-axis. Again, the same complication. Field lines and area vector are perpendicular, as you can see, and the flux is going to be 0. Likewise, the back face, this face here, the area vector was on the negative z axis, and the field line is perpendicular, and the flux is again going to be 0. So there are only two faces. There are only two faces on the cube that will experience flux. And what are those two faces on the cube that will experience flux? Those faces on which the field line is actually crossing, or we can say that the area vector is parallel to the field. So this face, the area vector is along positive x-axis, and this face, the side face, the area vector is along negative x-axis, and in both these cases the field line is either parallel or anti-parallel. So there is going to be flux through only two faces as they are shown in the diagram, this face and this face. And what is the, let's mark the faces. So let me mark this face as face 1 and let me mark this face as face 2 by the color combination. And let's talk about phase 1 first. So the flux through phase 1, I'll mark it as phi 1, will be E dot A, and since and that will be equals to E into A into cos 0. You can see what cos 0 is. Cos 0, why? Because they are parallel, area is along positive x-axis. Or you can write it other way around. You can also write phi 1 is equals to, what was E? Cx I cap, do you remember? And what was area? Area was A square I cap. And how is area A square I cap? We know that the value of this face is A squared because the side of the cube is obviously A. So obviously the area is A squared and the direction is along positive x-axis. So that becomes equals to Cx A squared, and I dot I becomes equals to 1. Now what is the value of this x here? What is the value of x here? So let me mark the face in yellow. What is the value of x here? Do you remember the coordinates when we were discussing the coordinates? Okay, so let me show this here. The value of this face was, let's mark the coordinates. This point was 2a comma 0 comma 0. Do you remember? This point was 2a comma a comma 0. This point was 2a comma 0 comma a. So we can say that all points have an x coordinate of 2a. And since all points have an x coordinate of 2a, it becomes very simple. The entire face has an x coordinate of 2a. So that becomes 2ca cube. That is the flux through phase 1. Now considering the flux through phase 2, this face here. So we'll write it as phi 2, again E dot A. And this time we will again write it in vector format, Cx I cap. And if you might understand that A is in the backwards direction now, you can see A is in the backwards direction now. So your area vector would be given as A square minus I cap. So Cx A square, and what is the dot product of I and minus I? That will be minus 1. And what is the value of x here? What is the value of x here? In order to find the value of x here, we need to understand the coordinates. So if you remember the coordinates of these points, this coordinate was a comma 0 comma 0, and this coordinate here was a comma 0 comma a, and this coordinate here was a comma 0. So you will see the x values of all 4 points is going to be a, and if the x values of all 4 points is going to be a, the flux is going to be minus Ca cube. And what does negative flux mean? Negative flux means the flux that enters. And what does positive flux mean? Positive flux means the flux that exits. So what will be the total flux? Phi naught. The total flux will be the sum, and that will be equals to C into A cube. And if you do remember the Gauss theorem, the total flux Ce dot ds was equals to Q enclosed by epsilon naught. So if we have the total flux, that is Ca cube, we will have Q enclosed, that will be equals to C epsilon naught into A cube, and that is the charge that is enclosed within the cube.